In Chapter 10, Section 5, Problem Set C, number 21, we're given this quadrilateral WXYZ that is circumscribed about circle O. That simply means that its sides are all tangent to the circle. And we're trying to prove that segment XY plus WZ is equal to segment WX plus YZ. Now, the proof to this, or the strategy to this proof, is going to use what is called the two-tangent theorem, which states that if two tangent segments are drawn to a circle from an external point, then those segments are going to be congruent. And so let's get started with our proof here. Well, we're looking for XY plus WZ. And XY is constructed of these two segments, XQ and QY. Now, what we're trying to show first of all is that XY is going to be equal in length to WX. Sorry, these are in backwards order here. So the first thing that I probably want to do is to rewrite them. I want to show that XY is equal to YZ. Now, YZ is also constructed of two line segments, ZR and RY. Now, using this two-tangent theorem, we can easily see that YQ is going to be congruent to YR. So what we need to show now is that RZ is going to be equal in length or congruent to XQ. But we do know we have a number of two tangent segments or tangent segments going along here. First of all, XQ and XP are going to be congruent because they are tangent segments drawn from an external point. Then PW is congruent to WS because, again, there are two tangent segments drawn from an external point. Then we have SZ is congruent to ZR because those are also tangent segments drawn from an external point. Now then, one way to look at this might just be to break each of those multiple segments into their corresponding parts. So for example, XY would be broken down as XQ plus QY and then plus WZ, which is WS plus SZ. On the other side, YZ is made up of ZR plus RY, and WX is made up of XP plus PW. Alright, so I think all we need to do here is to show that each one of these parts on the left is congruent to a part on the right, and that's going to be the basic strategy for this. So we know that YQ and YR, or RY, QY, and however we say that, these, QY, is congruent to YR, or RY. Next, XQ, now we can't tell that XQ is congruent to RZ in and of itself. However, we do know that XQ is congruent to XP, which happens to be part of the segment WX that's on the right side of the equation. So XP on the right is congruent to XQ on the left. So I hope you can see that there. Next, WS is congruent to WP or PW. So there is a WS on the left and a PW on the right. And finally, SZ on the left is congruent to RZ or ZR on the right. So we can see that when we break these segments down, each of the original parts, X, Y, and WZ, are made up of two component segments each. When we break them down into their component segments, we have 4 segments on the left and 4 segments on the right. And even though we can't show that directly that QX is congruent to RZ, it turns out that there are other pieces that will be congruent to each of those pieces in there. So anyway, that's the strategy to go about solving problem 21 in problem set C.